Okay, so since I cannot be here with you all today, I thought today would serve as a good use to review finding out if a vector space is a basis as well as the dimension of that basis. So remember, if this is vector S, this is our supposed basis, right? It will be a basis if it spans the vector space, which means any vector in the vector space can be written as a linear combination of those vectors. And also that supposed basis that we hope is linearly independent, which means the only solution would be the trivial one. So here's our question. Is this set of vectors S a basis in R3, right? Well, first of all, let's check out to see if it spans. Now, it will span if there is a linear combination A times the first one, B times the second, and then C times the last. So there's a linear combination of those vectors, and does that equal any vector in that vector space, u1, u2, u3? So we're trying to say here is any vector in R3 space. Can it be made up of a linear combination of those? Well, if we write out this system of equations that we have, 0a plus 4b minus 8c is equal to u1, 3a plus 0b minus 15c is equal to u2, negative 2a plus 3b minus 16c is equal to u3. And again, our question is there a solution for this? Well, there will be a solution for this if the determinant of the coefficient matrix doesn't equal 0, right? If it does equal 0, it means there's no solution. Well, I've already ran this on the calculator, and sure enough, the determinant's negative 45. So that means the determinant does not equal 0. So yes, there's a solution for this. So we are a spanning set. Next, we need to check for we need to check for linear independence. Now what that is saying is that instead of those vectors equaling u1, u2, u3, they would equal 0, 0, 0. And it would only work if A equals 0, B equals 0, and C equals 0. So I'm going to take that system there, and I'm going to put it into a matrix. And we know that we want to have zeros. I have my calculator solve this out, and it winds up with, calculator did it, this is the solution. That means A1 is equal, or A is equal to 0, B is equal to 0, and C is equal to 0. So yes, we are linearly independent, so we are a basis. Okay, let's look at one dealing with polynomials. Would this be a basis for P3, meaning polynomials of degree 3? Well, again, we're going to check to see if it spans, right? Does it span P3? And that means that A times the first vector, if I'm just going to call, well, I'll write it out. And then B times the second vector, C times the third vector, plus D times the fourth vector. And does that equal, any vector in P3 space, right? Which means there's a third power, second power, first power, no power. So there should be 4 terms. Well, what I did was, my next step was to collect all the, I distributed all this, right? And I collected the cube terms. Let me write out what I mean by that. So for our cube terms, we have this, right? We have AT cubed plus CT cubed. Those are our cube terms. And then our square terms are negative 2AT squared and BT squared. And in our t terms, we have 2 CTs plus 5 DTs. And in our constant terms, we have 1A plus a negative 4B. Now the thing is, if this equals any vector, right? So any vector out there would be a linear combination of those. Since it's polynomial, we're going to write it like this. And so what I'll do is I'll write this into a system of equations, right? A plus, let's see, there's no B's, but there is a C, but no D's. Now equals U1. If I look at the next one, I've got negative 2A plus 1B. And again, there's no C or D, so that's U2. And the next one, we have 2C plus 5D. And then our last one, we have 1A minus 4B. And we want to know, does this work? Is this a solution? Well, what we would do is we would go ahead and find the determinant of the coefficient matrix, right? So A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. Find out what this is. Now, I've already done this. I found that determinant. It equals negative 35. So this determinant doesn't equal 0, so there is a solution to this. So we are a spanning set. We do span the set. Now we want to find out if we are linearly independent, which in other words means when we do the same system, right? So A times vector 1, or polynomial 1 rather, and B times polynomial 2, C times polynomial 3, and then D times polynomial 4. Does it equal 0? And does it equal 0 only when A is equal to B is equal to C is equal to D is equal to 0? Well, what we do is take our system and put our solution in here, and we will have the calculator solve this out and see what we get. I've already done that, and this is what it kicks out, which means A equals 0, B is equal to 0, C is equal to 0, and D is equal to 0. So yes, we are linearly independent, so we are a basis. Now, as far as the dimension of the basis, that's the easiest one. Since this is a basis, it's made up of 1, 2, 3, 4 vectors, so it is a dimension 4. If I look at the one we did earlier, this was a basis also. It's made up of 1, 2, 3 vectors, so it is a dimension 3. Okay. So again, what you need to do on the assignment today, and I'd like you to turn it in before you leave, there's not many questions. Find out if those vectors you're given, are they a basis? And how do you find that? Find out if it's a spanning set, right? And find out if they're linearly independent. I will see you all tomorrow.